Okay, we're ready for our next speaker, Varoon Mathur from AI Now Institute. And his talk today is entitled Fair Machine Learning Tools for Electronic Health Records. Please welcome Varoon.
This works. Okay, perfect. Thank you so much. So my name is Varoon Mathur. I'm a technology fellow at the AI Now Institute. My background is in software engineering and machine learning, and before joining AI Now, which we're based in New York, last year I was previously with Microsoft as their data science for social good fellow. So I'm coming at, so what we do at AI Now is actually research the social implications of the technologies that we build, right? So the social implications of AI, how does that impact clinicians, patients, the whole system, right? So I'm briefly going to describe some of these larger tools that, to describe bias and fairness in machine learning algorithms. From our research perspective, try to give a higher level summary of that. I'll try to be as succinct as possible because I never know if I'm between you guys and lunch. But let's look at the sort of the field of fairness. I love showing this slide because it kind of shows us where we've hit our oh shit moment in the field. 2012 is when AlexNet dropped. That was the first deep neural architecture that then really took the computer vision field by force. Lol fairness, bias and fairness was kind of talked about as we need to watch out for the impact that these systems might have. 2016 and 2017, now everyone's talking about bias and machine learning. So here we go, right? What I want to do is I want to talk briefly about what kind of systems we see now, especially in the pharma R&D space, right? And then look at sort of the implications of those systems. So this is a paper from a team that did some research at Cincinnati Children's Hospital, which I think sort of does a good job of summarizing sort of the larger use cases for AI, or the dream for AI of revolutionizing at least what we want to see in clinical trials, right? So an AI algorithm that's able to understand which patients you would love to be pulling into your trial, right? This part right here, right, where you're looking at, you can take EHR data, electronic health record information, understand, are they going to say yes or no? Are they going to be amenable to the trial that you want to run, right? So this study was done in 2016. One of the things that they found was when they ran when they ran sort of their false error rates, when they tried to look at what kind of patient demographics were they failing, primarily black patients, right? So for them, they understood this. They looked at the data, said, okay, how do we readjust our weights in our model to make sure that we're accompanying and we're advocating and we're including the patients that we want, right? Equity, right? But what I'm going to talk about is where some of these problems occur with the kind of tools that we're using right now, right? So fairness, machine learning, biasing, right? I know a lot of people here have been talking about buzzwords, right? Machine learning, deep learning, buzzwords. I'm going to add another buzzword to your vocabulary, debiasing, right? I think we've heard a lot of data scientists over the last day or two talk about let's get rid of the bias out of models, right? Let's debias these models, right? And actually right now, in industry practices right now, there's a ton of tools right now to support data scientists to sort of debias their models. So you have IBM's AI explainability models, there's AI 360, which is an open source platform. Go in, they have tons of open source tools for you to check out how you're doing. What if, this is actually a Google tool. Google's what if tool is actually really cool. It allows you to understand what kind of people or data points you're targeting based off the model and the data set you have. Facebook even has a tool, but this I don't think is available for everyone. It's called Facebook Fairness Flow. That might be an internal use. I know this is the dream for a lot of us, right? I mean, a lot of data scientists out here are salivating at a Python package. If any data scientists have a terminal up, you can see if this is import. I don't think this is real, right? I wish it was this easy. Right? I wish it was this easy, right? And I'm here to tell you that it's not. And this is a figure from IBM's 360 AI paper, right? This is, I think, one of the better images that really describes what debiasing or what understanding bias in your models looks like right now. So you have your raw data, and you have 3 different pressure points during your model training that you can actively use sort of fairness metrics to understand how can you change your model in such a way that you're actually avoiding the bias in the model output. Fairness pre-processing before you're actually training your data, training your models, looking at your actual data set. During your training set, right? During your training, actually, leaving out certain protected variables, right? Same thing with post-processing. Once you have your model, you recognize there's bias, how do you go back, right? Because here's an interesting issue, is that, especially in this case, and I'll touch on this going forward, it's really computationally expensive to go back to your large data set once you've discovered that there's bias already, right? So this is a very attractive pressure point here for a lot of industry professionals. So what do I want to do during this talk? I want to talk a little bit about the mathematization of fairness and bias. I think this is the perfect crowd to talk about that because we're much more varied in experience. And that means I don't have to go into the technical weeds. And I'll talk about 2 case studies or case ideas that we, at least at AI Now, we've been talking about. Then I'm going to talk a little bit about the limitations of that in the context of using electronic health records to build predictive analytics and tools, right? And then after that, I'm going to talk a little bit about the research that we are doing directly, which is a social systems analysis of what that looks like. So this is a paper that's preliminary work that's coming out right now between me and Liz Kazunas, who's a very fantastic mentor and postdoctoral fellow at the AI Now Institute, focusing specifically on the sort of patient lived experiences with a lot of the digital technology that's out there. And so what we've actually been doing have been going through the actual clinical predictive tools that have been published in peer-reviewed journals, understanding how are they taking care of bias, and if so, what are they doing about it, right? And one of the things that we realize is that the idea about how they're making decisions about what metrics they're using to accompany patients is not really justified, right? There's a small subset of papers right now that actually deals with bias after building clinical predictive tools on their electronic health records, right? Smaller still are actual peer-reviewed papers that are talking about how they're coming at those decisions. So that's something that we're looking at. But this is the crux of it. Bias and fairness, if you mathematize a lot of these concepts, right? There are many different definitions of fairness and bias out there, and most often, are actually mutually exclusive. So Karen Howe is a reporter for the MIT Technology Review. This was a great piece of journalism that was done just under a month ago, based off of the COMPAS data set. I know the classical example of bias is the COMPAS algorithm used in Broward County, Florida, that found that it was predicting higher bail risk rates for black defendants than white defendants, right? And this was the classic example of an algorithm that appeared to be racist. And so what they did was they actually delved into the case study and to understand the competition between ProPublica telling Northpoint, which was the vendor of the algorithm, to say, look, the way you're assessing bias is wrong. And the dispute actually that Karen Howe actually sifts through is that they're using definitions of fairness, each of them correct in their own means, but you can't use them together. And the reason why is because of the inherent data set population metrics that are undergirding that entire system. What I mean to say is that at this point, any sort of algorithmic debiasing tool is not actually getting at the solution you want, right? There are competing bias metrics out there. This is from a slide from a couple of years ago, Arvind Narayanan, who's a researcher at Princeton, with a very famous talk, The 21 Definitions of Fairness, right? Now, this is part of that list. I couldn't include all of them. But as you can see here, individual fairness, group fairness, should everyone who has the same risk score act the same way in the model, or should demographics be treated equally, right? Should models be colorblind, so to speak, right? All of these are competing definitions of what you use, right? And so our research is looking at our clinical predictive tools that are based off electronic health records. Are they justifying any of the tools that their metrics are they using? How do they do that, right? So that's something that I'm particularly very interested in. This is a tweet. I'm a big Twitter fan, so I'm going to include some tweets. Ben Hutchinson, who's is a fantastic fairness and machine learning researcher at, I think, Google, has a really great paper called 50 Years of Fairness Definitions, which is actually showing you that there's a long history between fairness metrics, and it's not grounded in machine learning and AI. It's much further than that. And this is quoting from a paper from 1973. So you can see this is a growing problem that machine learning right now is still not addressing, at least from our research and what we see right now. So that's competing definitions of bias that algorithmic assessments just can't get to, right? But there's another layer to that, and that's when you're developing your models. So I know Chris Curry, who was a keynote yesterday, pointed this out, and I'm still going to point it out today. This was a recent science paper by Ziad and a team at Berkeley and a collaborative team who got a data set from a health hospital system and realized that the risk score predictive, the predictive risk score based on that data set was biased for black patients because the model was using cost of care as a proxy variable for understanding, are you going to be at risk for chronic illness, et cetera, right? The problem is we spend less money on vulnerable and marginalized populations, at least in this system, right? So now your model is skewed already, right? Now, this is an example. This is a fantastic paper, and I encourage you to delve deeper into it. But I'm using this as an example to show you that there are proxy variables in the data sets, right? So there are protected groups like gender, race, et cetera. And it's part of the debiasing aspect, at least from a data science point of view, is, okay, let's just remove them from the data set, right? Train our models, right? And now we can effectively say that we're building machine learning models without looking at gender, without looking at race, without looking at, well, that's actually wrong, right? What we're actually seeing, and this is another class of this, what we actually see is that machine learning models are, and I'm going to give them credit, actually smarter than we think, right? Because what they're able to do is understand secondary variables as proxies, right? A clear-cut example of this is your zip code, okay? More often than not, if you're using geographic data to understand where patients are coming from, your zip code is more likely or not going to be a proxy variable for your race, right? History of segregation, right? Redlining. This is classic, right? So your machine learning models are going to pick up on this. Just because you don't include gender or race or whatever protected variable in your data set doesn't mean it's not going to show up, right? This is another issue where, as a data scientist, I can't get to. There's no level of APIs that's going to allow me to dig deeper into that, right? This is a bigger problem than that. So where does that leave us with electronic health records specifically, right? Where is our research looking at sort of the limitations that exist based off of at least the two case examples that I provided? So these are two papers that I wanted to highlight that dive deeper, not into sort of what are the digital constructs of electronic records and how you can conform that into actual data that you can use for machine learning models. It talks about sort of the caveats with electronic health records, right? And both of these papers actually delve into ethnographic data. Like, this is classic social sciences. This is speaking to patients directly and hearing their stories, right? What are the things that we hear, right? There are gaps in individual patient records because of healthcare disparities, right? More often than not, some patients are going to be treated others than likely, right? People of color are not going to get the same kind of treatment, and they're not going to have the same patient-physician relationship in some communities. I mean, this is a fact, right? And electronic health records are actually capturing that, the lack of it, right? That's a problem when you build your models, right? Omission of behavioral health concerns due to stigma, right? How is EHR data capturing behavioral health data, right? More often than not, or physician asking specific questions, right, and a patient responding in a certain way, right? There's an underlying fact there that in EHR data is not going to get to. I don't care what kind of voice assistant you use, right? That's not going to show up. Underreporting of chronic pain due to cultural factors, right? How do some people report their pain, and how do some people communicate, that aspect of their life to a physician, right? That doesn't get coded in EHR data as well, right? So now when you're building models, it's not enough to just say, okay, how many black Americans are we getting in our model system, right? There are underlying social factors out there that your model and the data science is just not going to get to. And this is a fantastic paper by Liz from AI Now, who actually goes through this specifically with the diabetes community, right? I encourage you to check that paper out as well. There's another issue at stake here, and it's called trust, right? How do I trust where my data is going to, right? We talked about trust before. We talked about trust from the fact of a physician wanting to trust the model output for a predictive score. Well, patients also have a trust issue too, right? This is a recent study that actually showed that de-anonymized data between two different data sets of EHR data can actually be linked together, and I can find out who you are, right? That's de-anonymized data, right? Here's another example. This was actually in the New York Times, right? I can get a cross-section of your MRI from your head scan, right? And using generative models, which is, models that are able to learn based on the training data and then generate new examples, right? I can a team actually was able to show that just using the cross-section MRI of your brain, I can actually generate your face and I can identify you pretty well, right? Just from the MRI image. I don't need any metadata, right? That is going to affect patient-physician relationships if patients understand this. Now, I know this dropped yesterday, and I know people are going to be talking about it, but the Wall Street Journal reported about it, and I find that pretty interesting. But Project Nightingale, right? This is Google. I mean, this was the report came out that Google was, actively getting and gaining electronic health record data from different hospital settings. Patients who are not able to access their own information, but also don't know who is able to access that information, right? That level of trust is also going to seep into your EHR data because that is going to affect how they report further and further on their outcomes, right? So trust as an inherent factor for patient-physician relationships that then get modeled in EHR data, that's an issue as well, right? And it's a part of the limitations, part of the larger ecosystem. Okay, so I've talked a little bit about the gloom and doom of these things. But sort of what are the forward-looking aspects of this? And this is something that we're working on at the AI Now Institute, right? So a social systems approach is an approach that takes the focus on the sort of data science teams out into what are your values as an organization when you're building these tools, right? So what we found so far is that when you're starting to build teams that build predictive analytics, you're not just focusing on sort of domain expertise, right? Your biomedical expertise, your experts, right? There's a larger team here that you can actually encompass, right? And we found that any sort of scholar or expert or team that has an understanding of the social, political, cultural impact that these systems are going to have, that's incredibly valuable, right? This allows you to understand sort of the larger questions that are looming at the forefront, right? I spoke before that bias is really hard, computationally expensive to redo once you've trained your model, right? That's a lot of dollars gone to a model that you have to retrain, right? Incorporating a social systems approach might actually give you the edge to understand where some of these larger threats are coming from. So an example I'll provide is from another paper that we're working on. Sarah's also another postdoc at the AI Now Institute focusing on gender discrimination in AI systems. And so what we've done so far is looked at fairness limitations in inferential phenotyping systems. Now, inferential phenotyping, what we've defined, are any predictive systems that will try to make inferences about your character, personhood, whatever, just based off of your appearance, right? I'm seeing heads nodding and everything. You guys are seeing the problem that's going to come up. So things like automated gender recognition systems, emotion recognition systems. There's a slew of these. McKinsey, I think, had a report that this is a $1 billion market now, specifically emotion recognition systems, because we want to understand how people feel about different products, right? So on the left here, this is a pattern diagram from Intuit. I included this diagram here because I think this is a really great diagram that kind of exemplifies what we're talking about with inferential phenotyping. You have this is from a phone interface, right? You smile at the phone, right? You have facial landmarking on the face, right? And it's able to tell you, oh, you have 100% joy, right? And so part of this is the inferential, this is emotion recognition, right? And so part of that, what we're seeing right now is that there are inherent problems with this. And I know somebody mentioned, I know somebody mentioned it yesterday on a panel, but this brings into effect what we talk about versus causal inferences and correlative inferences, right? This model right now is saying that it's 100% joy because more often than not, the way the facial landmarking systems arise, that looks like a smile, therefore that's more likely joy, right? But this could also be a face of just pure terror, right? model's not going to pick it up, right? There are underlying cultural factors in this kind of recognition systems that this model is not going to pick up, right? So at the end of the day, a data scientist that has this problem in front of them, a PM that has this specific mandate tool in front of them, there is no way that they're going to get at the causal inference problem, right? Because there's always going to be a population that's going to be marginalized and discriminated against for the system, right? Imagine somebody having some sort of illness where their face is not able to make the same moves, right? They're not going to be able to use the system, right? Disabilities, accessibility. And on the right here, what you're seeing is an excerpt from a report, I think from also the Wall Street Journal. That's interesting. And I think, so recently, the FTC has been cracking down on a company called HireVue. HireVue is a vendor that provides tools for companies that are hiring remotely. And what they do is they allow for an AI recognition layer on top of that video conferencing mode, right? So now, as a company, you're able to understand that specific facial expressions, the way, the intonation between other people speak, everything, that could give you a good insight into whether or not this person might be a good fit for your team, right? There's inherent problems with that, because at the end of the day, that data set's being constructed, but what is the undergirding causal model behind that, right? It's all stats, and that is not going to tell you the ground truth, right? This is an example in which a social systems approach would probably kill this project before it started, right? At the very least, you would have ethnographers or social scientists talking about Ekman, talking about the history behind eugenics, that would have said, look, at the end of the day, this screams a lot of the sort of larger race sciences that we've seen very much in the past. We don't want to be associated with this. This is not a good model, right? Right. Now, there's arguments to be made about whether or not you want to continue on that path regardless, but at least a social science approach, social systems approach would have called this out in the beginning, right? So at the end of the day, what are we seeing as who's responsible, right? Who's responsible for a lot of these outcomes? Is it the data scientists? I think there was a presentation this morning that talked about .data said, you know, we're giving data scientists too much responsibility. Or we want them to do this much. They can only do this much. And I say I agree, right? I think they're ill-equipped right now to handle bias and fairness as we know bias and fairness to be, which is not fairness, it's justice, right? What does that look like, right? Mandate for analyzing and assessing algorithms, it's going to be coming from top down, right? It's got to come from management, it's got to come from your values as an org. I think that's, at least from our research, that's what we're seeing, right? When it is mandated or when there's an ethos that seeps into all the teams, that's when we see those productive changes, or at least that's where we see the incorporation of that, right? And as mentioned before, domain experts are not simply enough. Who actually is the domain that you're trying to get at? What are those experts about? What do they bring to the team? That is actually the nuance behind that makes all the difference, right? Right. So sometimes, more often than not, patient advocates, right? Ethnographers, anthropologists, right? This team is going to be much broader than you think. So I'll just end off here. At AI Now, we produce a report every year. It gets a lot of traction, and we're working on ours right now for 2019, but this was from our last year's report. Talking, again, about the limitations of sort of the mathematical ideas of bias and fairness. And I've highlighted a section, you know, without a framework that accounts for social and political context and histories, these mathematical formulas for fairness will always inevitably miss key factors. I think from our research, from what we've seen so far, this continues to be the case, right? Bias, debiasing is going to be a buzzword we're going to see in the 2020s, right? And this is our way of saying, hey, hold on. We have a real issue that we want to address here. Thank you so much for your time. I appreciate it. I'll take any questions after, and I'll be hanging out a little bit. Yeah. I mean, I agree with you in some sense. I think they're very much correlative, right? I agree with you that an AUC curve is not going to really tell you about patient overall wellness after the model's been implemented, right? Your clinical endpoints are going to be different, right? Your AUC is not going to, your F1 score is not going to address that, right? I think there is bias, though, in deciding what metrics to use for success, right? So fairness can also be what equity looks like, right, for a patient going in that system. And maybe it's not the actual prediction of that model, it's how that model changes this entire ecosystem around that care, right? And how does a patient from different socioeconomic backgrounds move and maneuver through that? Why would you even put such a proxy bias in the model? Most of the time, it's obvious to a data scientist that should not be in the model. Honestly, I kid you not, it is not always that obvious. It is now, all right? But let's not every data scientist is woke. So what do we do to introduce biasing variables into the model for segmentation, but not use them in the same way as others, aka? So this is a tough question to answer, but I will talk a little bit about what's currently state of the art. So if anybody knows Luke Oakton-Radner, who's a radiologist in Australia, came out with a recent paper called sort of the hidden stratifications of image segmentation. So your noisy labels on your data set, right? What you're actually tagging as sort of these overall disease markers, you need to go a step further, right? What are the actual other underlying risks, right? So actually creating much more richer data sets in a way that actually encompasses sort of the larger disease standpoints has actually been an interesting sort of maneuver when we talk about auditing algorithms, because it actually makes it easier for others without expertise to go in and say, okay, we need to audit and open up this algorithm because, from a clinical trial or from a regulatory perspective. Anyway, that's my 2 cents.